Yeah, a student asked me about the dynamic programming uh, algorithm for proving the Kleene start, A start, is in P if A is in P. Okay, so I can understand it could be a little bit confusing because in this problem we are not doing any optimization, but we do have a recurrence relation. So that means that if we understand dynamic programming, it is just a general approach using memorization to solve recurrence relation. And the time complexity analysis really depends on two things, right? So one is the number of subproblems. The other one is the number of dependencies in the recurrence relation. So if you remember that when we talk about subproblem graphs, so if you look at the graphs, okay, the vertices are different subproblems and the edges are dependencies, and then of course the total runtime would be the dependencies times, so that's the dependencies, the number of dependencies times the number of nodes. Okay, so that's a running time. So now I'm going to go over this problem again. So here A is any language, okay? A is any language, which is polynomial time computable or acceptable. So of course, in general, A is infinite, right? And then A star is the set of strings. Let's call it Z. So such that Z can be broken into several pieces. Let's call them Z1, Z2 up to Zk, where each Zi is in A. Okay, so that's A star. So for any Z, so if you think of this, so this is a Z, then you can break it into different portions, several portions, and each of these is in A, which of course could be a single symbol or could be a string, right? So each of these is in A. Okay, so that's Z. So in this definition, we don't have a recurrence here. So, but we can change this definition to have a recurrence. So that means that Z is in A star if Z can be, so you can think of, I break it here. So this portion, we know by definition is in A star. So that means Z can be written into, can be written as X concatenate Y with X is in A and Y is in A star. So then now we have a recurrence coming in. So that means if you're given input, we first look for a breaking point. This is sort of like a cutting rod problem, right? But cutting rod there, we have an optimization in here. We just want to know whether This is not optimization. We just want to know whether this string belongs to A star. So in order to determine this belongs to A star, so we first look at a cutting point such this part is in A, and the remaining part is in A star. But we don't know the cutting point, so that means that we have to try all possible cutting points. Then, of course, this is a subproblem. This is a subproblem because we want to know. So this is, so let's say, so y starting from this part, we want to know whether this is A star. So this is a subproblem. So how many subproblems do we have? So we have, if given input z, the length is n, then we have n subproblems. So problems. So what's the dependencies? So here it depends on, let's say, this is what we have, right? And then it depends, so because we're going to try all possible breaking points. So the first breaking point is just this. This itself, the original string itself. And then we're going to break this here. So I want to know whether this part is in A, and then the remaining part is in A star, and then get another breaking point, get another breaking point, and so on. So that means the dependencies is also linear. So linear dependencies. Meaning if my subproblem starts from here, let's call it I to n, then I'm going to have n minus I many subproblems. So that's linear. So altogether, then we have n subproblems. Then each time we depend on linear, the many subproblems. So of course, it would be if checking something that's in, whether it's in A, we know it can be done in PA of length of x, right? So checking a prefix, whether that prefix is in A, can be done in time PA of length of x. So then, of course, what we really have here is that the time bound, we got to check, but for each subproblems, we're going to check, and we have the dependencies. So that means that we are going to have PA of n times n squared. And this is the upper bound. So this is a polynomial. So which means that by looking at the recurrence relation, that we actually know that A star is in P. Okay, so next we are going to just write down, now this is the recurrence relation. So we have the general approach of top-down approach using memorization, and also in this case, it can be done in a clever way using bottom-up approach. So we're gonna see these two. So top-down is to use memorization by keeping a array that computes, that stores the intermediate results. So we are looking at a subproblem. So the subproblem is start from I to N. So that's a subproblem. So I'm gonna call this KC of X. So this input is X. And we have a Turing machine that accepts A, so that represents A. And subproblem starts from Xi to Xn, or the subproblem is IN. Okay, so we could assume at the beginning, okay, or memoir is upside down T, and we can assume that is M, I'm sorry, we assume that N plus 1 N is 1. So N plus 1 N is 1. Okay. So then we know that the standard approach, we will check, see if so what we are going to return is to return this, to see this subproblem is in A star or not. So if memo I is not upside down T, we simply return, which means that it has been computed. Then we just return this. Otherwise, okay, then we are going to move up J. So this is a problem. J is from somewhere. Okay, so else we're going to do the recursion. So this will be for J from I to N. Okay, we check if X, this will be I to J. So that's this portion. This portion, sorry. Whether that's in A, which means that MA on this input is equal to 1, and this portion is in A star, so that means KC X MA J plus 1 N is equal to 1. If this is true, then we know if this is true, then I know that memo of J is 1. So this means that memo if this is true, memo I is 1. If this is not true, then it is not, so it is 0. Okay, so that means that this, if you cannot find such J, such that this is the case, so this is a return. So when you find 1, So actually J, okay, so we change this to J. One is 1, the other one is 0. Okay, so after you're done, we are going to, after this loop is done now, so you know that, so we keep moving this J up. Okay, so, and then we return, finally we return memo I. So this, we still have a recurrence, okay, but we could get rid of recurrence using, so this is a bottom-up approach. So what we are going to do is single list my array, this for memo, this is n. And then I'm gonna have a dummy node on the right indicates this is empty string. So empty string is always in A star. So I'm going to set it to 1. So that means T n plus 1, T of n plus 1 is 1. Okay, so we're going to have KC, which is, again, X M A I N. So initially, set Tn plus 1 is 1. And then I'm going to assign everything else to be to 0. So for j from I to n, okay, we let t of j be 0. All right, then for j from I to n, well, since we get rid of recursion, so j will have to be moved from bottom up. So this is the bottom. So this is the bottom. So that means my j will from bottom up. That's n to I. Okay, so whenever I have, let's say my position j is here, then I'm going to look for so then I'm going to look for k from j to n. Okay, so j will move from bottom up, and then k will look for from j to n. So then I'm going to say if for any fixed j, so we want to know, see, this is in A, the rest of it is in A star, and then so for k from j to n, so if, so of course it, and then we're going to look for this portion Okay, so just keep looking at all possible subproblems, and then we assign their values. So for k from j to n, if ma xi k, this is equal to 1, which means that it belongs to A, and t of k plus 1 is 1, so which means then t of k t of here, excuse me. So this should be from j to k. Okay, so the idea now is this. We want to know okay, so we know the recursion. So this is the bottom of the recursion. So my j from here, and I want to know whether this portion is in A star. And then I'm going to move down, and then I want to see whether this whole portion is in A star. So in order to show a portion of which is in A star, so we want to know, so again, we want to break it. We try all possible breaking points, so try to see whether this is in A, this is in A star. Okay, so that's what this means. So if xj to k is 1, that's in A, and tk plus 1 is 1, so that means the string after that, the suffix, okay, is in A star. Then we know that, so if this is true, so this is, so k, then tk is 1. Okay. K from j to, so actually this should be j. Okay, so once again, the idea from bottom up approach is this. So we're looking, so j star from bottom, that's n, and then all the way up to I. Okay, so we first determine whether t, so what t of j is. That means what t of n is, meaning we want to know whether x and so the last symbol is in A. If it's in A, then of course we know it's in A star. So then J will move down a little bit, one more cell. So now you have two symbols. And then one way we look at here is that we want to know whether this whole thing is in A. Okay, and if it is, and we know this is 1. So if this whole thing is in A, then t of j is 1. If it's not, so if this whole thing is not in A, then I'm going to look for to see whether, so whether, sorry, so we first look for whether this thing is in A and whether this is 1. Okay, so either this is when only this is in A and this is 1, then then T of J is in A star. So if it's not true, then we're going to look for this, the whole thing, to see whether it is in A, right? So that's what this loop is. Okay, so finally we return T of I. So then we can get rid of the recurrence. So that's it. So that's the that's what this bottom-up approach looks like. So let me erase this. And the idea, once again, the bottom-up is the bottom is starts from n because that's the end of the recurrence. So we start from bottom. So J start from n, move all the way down. Now this is already determined, and then we want to decide what the value of T of n, and then we determine what the value of T of n minus 1. So if T n minus 1 is 1, so that means this portion, this suffix, is in A star. And then we continue to move down. Okay, so for each J value, so that means here, when we are here, so this is J. So that has not been determined. Now we have all the value in here already determined. Okay, so including the last one, always 1. So in order to determine this, we first see whether this guy is in A, and this is 1, because if it is 1, that indicates this portion is in star. If it is, then we set it to 1. And so then we are going to, if it's not, then we are going to continue to look for this to see whether this is in A, and look for this to see whether this is in A star. So we keep on doing it. Okay, so that's the bottom-up approach.